Hi everyone, my name is Julien Villamasson. I'm from France, and my partner Mathieu Richard and I founded Dynamik Orbits 5 years ago. It's a small company where we model constellation of satellites around the Earth to help the industry know where to place satellites, where to place ground stations, and things like that. So it's just the two of us in the company, but we've been working for 5 years on this. And as a side project, which is not commercial or anything, we started to model a constellation of satellites that orbit the sun to create an internet connection between the Earth and Mars. So we'll talk about the different architectures that exist, and then we pick two architectures and we analyze the performance for Earth-Mars communications and also for ships in transit. Because if you have a spacecraft going back and forth to and from Mars for 6 months, you also want them to have an internet connection. So the premise here is that maybe this will be in our future. So if you believe in that, or if you want to know this is one of the possible outcomes in the future, then an internet connection between the Earth and Mars will be really useful. Think of many robots operating here. Not all the data needs to stay on Mars, and there will be a lot of remote control and stuff like that. Well, data passing back to Earth. So it's really a critical infrastructure, that internet connection. So first of all, I'm looking here at the existing links between the Earth and Mars. So of course we have the direct link option, which gave us 6 megabits per second maximum, but 0.5 at the furthest point. We have a relay already in place today, but that's satellites orbiting Mars, relaying with direct links back to Earth. And then we have so that's all RF, and we have also optical link with the mission Psyche that provided at the distance that we're looking at also 6 megabits per second. So it's not a great capacity that we can really work with. And the problem, of course, is the inverse square law, meaning that as you go further in distance, then the throughput gets decreased. So here we're plotting the 3 measurements from Psyche, and we see that it follows very well the inverse square law. So if that's Earth and Mars, and that's kind of the capacity you can get with a given system, as you go away from the planets, the capacity goes to almost 0. So say you start with a gigabit per second, 100 megabits per second is pretty close to that. Then as you go further, the capacity really drops quickly. So you need a set of relays. If you could have a set of relays, you stay in that colored area and you stay at maybe 100 megabits per second or 10 megabits per second. But of course, those 4 relays here are not feasible because of the orbits. So you need, of course, a lot of relays, and that's the work that we are doing here. Just for you guys to know what sparked this interest for us is this tweet that showed that NASA is asking companies for a relay constellation, and Blue Origin, Lockheed, and SpaceX responded. But SpaceX said, we're going to do 1 gigabit per second to start, and then we'll do more than that. And I was like, whoa, how is that even possible? So we started to model it. As I explained, there's direct link. So that's not really possible if you want 1 gigabit per second. You have the synthetic aperture route, where you have a bunch of satellites at Mars and at Earth, and they kind of combine in a coherent or incoherent way. And there are some technical limitations to that. So I'm not sure this is realistic for the next 10 to 20 years. And then we have the relay constellation. The only drawback of the relay constellation is that you have really many satellites. It costs a lot of money, potentially. But that's what we're going to look at. We have 5 design goals for this. We want a high capacity, but also not just high capacity to start with, but also the ability to scale to even larger capacities. So we start with 1 gigabit per second, and then we move to maybe 1 terabit per second, even 1 petabit per second. I know it sounds insane, but that's the goal we have here. The latency must be low. We need to have a good coverage, meaning no conjunction drop or blackout, but also the spacecraft traveling need to be able to connect as well. It needs to be feasible, and the cost needs to be affordable. So we made a simulation at the website marslink.io, and you can go in there and model your constellation. I'm just giving you a 1-minute video to give you an example of what the website looks like. So these are all the satellites, and there's a link between each of them. So as you zoom out, you do not see satellites anymore. You just see like lines. So those are the links. Okay. Yeah, the website will then calculate the capacity for each line, and then the flow. We simulate a flow of data going from one planet to the next. And this helps calculate the actual performance of the system, not just the theoretical one. Okay. So how does it work? You have three main components of this network. You have in the middle the relay network. So from here to here, all those, they're less dense, but they can carry the data between the two planets. And then you need here and there, you need planetary rings. So it's a ring of satellites, which are more dense, and then they can carry more data. And on the left side, you can see the satellite view. So you see points, dots for satellites. And on the right side, you remove the satellites, you add the links between satellites, and you see the link view. It's essentially the same thing, just looking at the links here and satellites there. But if you unfold this and you make it, instead of circular, you make it flat, it's the same thing. On top, you have the Earth ring. At the bottom, you have the Mars ring. And you just take data, deploy it, transmit it through the relay network, collect it back to Mars. So there's two paths for each planet. In some situation, you have 50% of the data coming this way, 50% of the data coming that way. And the bottleneck is really these satellites right there. That's the most critical satellites. So in terms of the architectures, we figured out there's two main families. One of them is the concentric ring family, where you have a bunch of concentric circles, like we saw on the last slide, like this one on the left side, that is concentric, and that gives you a bunch of parallel routes, radial routes, and maybe each of them here is 2 megabits per second. But if you have 100 of them, that's 200 megabits per second, because you aggregate all the routes. You're not looking for the shortest path, and that's the only one that is used. No, you use all the routes together. You aggregate them. And then you have the other family, which is the transfer rings family, because it's really like Hohmann transfer rings. And the beauty of this is that there's a lot more density, so you can have a higher capacity between satellites here, but you have only two routes here, one here and one there, two orbits, kind of with a similar number of satellites in total here. But if you increase the satellite count, then you have more parallel routes there, and then you have more transfer orbits there. And the goal is to understand what is best and why. So if we do a high-level analysis of this, they each have advantages and drawbacks. And so at the end, maybe the best is a mix of things, but the transfer family with few rings, the best is that it has the best capacity for the number of satellites. So if you give it a number of satellites, it will give you like the best capacity possible, so it's the lowest cost. But it has a very poor latency, because the data needs to flow through the entire solar system before it can reach the planet. And also, it's not very resilient, and it's very bad for serving ships that are transiting between the Earth and Mars. So these guys, the ships, will not have any coverage at some areas. If you look at, if you increase the number of satellites of this same family, then you reduce some of the drawbacks, but it becomes very expensive because you have too many satellites. And then the last one is the concentric family with more satellites. And this one has like a lot of advantages, but then we'll see which is the best. But first of all, I need to talk about the laser technology, because all this is based on the Starlink laser link technology, and the baseline of that is 100 gigabit per second for 3,000 kilometers. And we expect that, if a company ever deploys such a system, they will improve the performance of the laser technology by, using any of those means. So increasing the aperture or the transmit power or things like that. But the question is how much will they improve the technology? So SpaceX is a baseline. TSAT is 70 times this capability, and Psyche was 90,000 times. But Psyche is very high cost endeavor. It's a one satellite, so it costs a lot of money. Here, the goal is to do mass manufacturing so that the same benefits as Starlink can be achieved. So we don't know exactly where we're going to end up here. So we take three different assumptions. One is 16x, one is 120x, and one is 1024x improvement. And we're going to look at those three. It might be a lot more. It may be like 10,000x, but we also want it to be low cost, so we don't want to go too far out. Okay, now that's the result part now. So on the left side, you see the laser tech factor is 16x. So that's a more conservative approach. And if you want 1 gigabit per second, then the two-ring transfer is 28,000 satellites, which is achievable. Starlink today is 10,000. They're going to 30,000. So it's something that humanity could achieve. But as we saw, it's not necessarily very good for latency and for ship coverage. So here, the best is the concentric approach. And if you want to go to 10 gigabit per second, 100, 1 terabit per second, then you need to increase the satellite count. And as you do that, you see that the lowest count is always the two-ring, but then concentric kind of becomes more expensive than the 40-ring transfer orbit type. So as we do this analysis for better laser technology, we see that we need less satellites. So for just 1 gigabit per second, we can just have like 10,000 satellites, 11,000 satellites, which becomes really realistic. And then as we move to even a better increase of 1,000x, then we need like 3.5 thousand satellites for just 1 gigabit per second. And if you want like 100 gigabit per second, then you're still at 35,000 satellites, which is not so much for such a performance. So it seems that this is it starts to be doable. Now, looking at the latency, the way we do this is we look at the four different positions, like conjunction, opposition, and then 90-degree offsets, gives us 4 geometries for each, and then 8 geometries for the 90 degrees offset. So we look at, it gives us a representative topology for the planets, basically. And as we do that, so this is the latency, and if you go to 0, it means 0 minutes between the Earth and Mars. Of course, it's not possible. But so if you're in opposition, then the direct link is going to be like this line here. So it's like 5 minutes or so. And with the concentric rings, you are at that latency. So it's the best if you want the best latency. The other systems give you a really poor latency. So maybe your best system has at least some concentric rings so that you can get good latency when you can. Some application will need that. Maybe 10% of the application needs good latency. Maybe 90% is just bulk data transfer. That only needs a lot of capacity, but not a good latency. Now, the other way to analyze this is the in-transit spacecraft. We want them to be connected. So we have 2 ways to do this. One, we have Monte Carlo probes. So we just scatter them randomly in the space available where we expect the spacecraft to be at some point, and we see how well they do. And the other one is we actually, and you can go on the website and just move through time, and every launch opportunity, there will be more and more spacecraft flying. You can see here the flight path, and you expect a normal distribution on the launch window date, and you can set how many days is your delta day before and after. And then the spacecraft are the blue points there, traveling to Mars. And then we can, excuse me, we can then calculate the coverage, first of all. So we see that for 2 rings, it's not good. Only 43% of the ships get access, so that's not acceptable. But the other 2 configurations work out well. Then for the capacity, the transfer family with 40 rings give you 2 times better capacity than the other one. So that's a good result. You get 13 to 20 megabits per second average. And in terms of the latency, the concentric gives you the best latency. So again, a mix of things maybe is the best. That's a video of like the website putting the Marslink satellites on top of us, and that's the spacecraft flying to Mars trajectories. So the yellow is not laser links, it's just a trajectory. And you can see Mars here humming along, and the spacecraft going to meet it sometime later. And then you see the links going from the ships to the relay network. And when there's no link from this one, it's because those two are actually connected together. So if you have like 5 or 10 ships nearby, they will just connect together and share one link if there's no other link available. That's the way we think it's going to work out. So that's kind of almost the end of the presentation. And I just wanted to think of the recent news, about the AI data centers in space. And so it seems that some companies, not to name SpaceX again, wants humanity to become a Kardashev 2 civilization. What they mean really is we want to put a bunch of satellites in space and get solar energy because we think this is the cheapest way to do AI for some applications. So fine. So once you run out of space around the Earth, around the sun you have a lot of space. So I was thinking, which is the best place to put the satellites, and is that Earth ring that we need in the Marslink system. And an AI satellite is really like compute, solar radiators, and then laser links. So you already have your Marslink ring there, and that's paid for by AI. So that reduces further the cost of your system, of your Marslink system. And yeah, so the way that I think the company could implement that is first to have the AI satellites deploy in Earth, in the co-orbit, the Earth co-orbit. Once we have this, then we deploy the other satellites as a concentric ring. This gives you good latency. This gives you a low cost. And it covers all the ships in transit. And once you have that, then you deploy a V2, which is the transfer ring, with only 2 rings. And that gives you 1 terabit per second. And if you expect like the middle scenario of 128, then the cost for the V1 is $12 billion. That includes the satellite manufacturing and the launch. $12 billion for a company that is well capitalized is achievable, probably, especially if they want to put like a lot of hardware on Mars, and they're going to need that connection. So it's a requirement. So $12 billion, maybe it's something they can afford. And then for V2, if they develop the laser technology, they can get it at 80 billion, which is more expensive. But at this point, they will ask themselves, do we need more capacity? If they do, that is the lowest cost way to achieve that. Thank you very much.
Okay, few minutes for questions. Fascinating talk.
Thank you.
Go ahead.
How did you secure funding for this research?
No funding. I just did it in my spare time.
Okay. Wow, that's amazing.
Yeah, I started about a year and a half ago.
So I have a comment question. So I work with Mars rovers, and your concept of poor and very poor latency to me would be outstanding. So what if you were to accept longer latency, hours, a day? I mean, lots of data that are needed could wait that long, right? Maybe some tactical small amount would be fine, would be fast. But how does your number of satellites scale if you're willing to relax latency by a lot?
Yeah, we can explore this, in more detail. But essentially, the worst that you can get with this system, is 70 minutes. You cannot do worse than that. I'm sorry.
So you're saying even with if you scale back the number of satellites, you're not going to?
No, it's not going to affect the latency so much. Yeah, the worst case is really this one. You cannot do less, even if you have less satellites. Just the topology of the rings This is the lowest cost, whatever the number of satellites you choose to have, and the worst latency is going to be 70 minutes.
Well, then maybe you were underselling latency. You should know that that would still, even an hour would be considered great for many applications.
Yeah, well,
You're calling it poor, very poor.
yeah, well, it's comparatively to others, but remember, we're just doing a very simple analysis of something, probably taking into account like 20% of all the factors that we should, doing our best with that, but we're not going to build it. We don't have plans to build it. You know, it's just theoretical at this point. But I really expect SpaceX will do this. That's the reason I'm interested in doing that.
You're hoping to buy your company.
Sorry, say again?
You're hoping to buy your company.
No, not really. I mean, yeah.
Any other audience questions? I have one more for you. But, go ahead.
What is the size of the satellite? I mean, is it Starlink-like or is it bigger? And because you know, the further you go from the sun, of course, you need bigger solar array.
Yeah.
So did you think about this in the design? And also, when you know, Starlink satellites told us about disposal, so they cannot stay.
Yeah.
Forever. So how about the disposal of these?
Absolutely. So in this study, when it comes to the solar arrays and the radiators, if you go to the website with the modeling there, it will take into account the orbits to size the solar and to size the radiators. So if some satellites stay in the Earth ring, they will have smaller solar panels, bigger radiators. If they stay at Mars, then the opposite. And for concentric rings, they stay always at the same kind of distance from the sun. So it varies, but less than if it was like a big eccentric orbit. So these ones will have worst case for both solar and radiators. But if you go to the transfer ring family, these satellites, they go from the Earth side to the Mars side always. So they need to carry the largest possible solar and the largest possible radiator. So these are more expensive satellites. Now, if we think of the Earth ring satellites, these are similar to Starlink satellites. They need the same kind of solar, probably a little bit more, but not a lot more. And they need more intersatellite links. When it comes to the relay satellite, we expect 4 laser links instead of 3. So it's 1 more, but it's doable. However, there will be bigger laser terminals, probably, a larger aperture, maybe instead of 15 centimeters, maybe 30. I don't know how they would be able to do that. But yeah, larger laser links, only 4 probably. Now your question of disposal of satellites, this study includes the return of the satellites to Earth. That's included in the propellant budget. I'm not saying that they will like demise in the atmosphere or they will be caught by starships or how, but at least we know that they're able technically to come back to Earth for disposal.
How long can they stay in the
I'm not able to answer this properly. I've not done a study on hardening and things like that. But I put like a 10-year design life for this system. So every 10 years, you replace satellites. Like Starlink, it's a 5-year cycle, so this would be more a 10-year cycle, I think.
Maybe one last question. Do you factor in the ground data system costs, your cost estimates, the receivers on the telescopes on the ground?
Yeah, so the way this works is it uses just Starlink as the receiver, Constellation. I did not have time to go in detail. There's a few more orbits near the Earth because there's too much gravity. So they're not able to maintain a station for the 10 years. And these satellites, I suspect, would be more specialized so that they can connect to Starlink. But there's no infrastructure to add on the ground. It just connects to Starlink. That's what I think SpaceX will do. Again, I don't know.
So I'll throw one more question in. You talk about Psyche and DSOC, 90,000 times better. But ultimately, it looked like from your trends, the better your performance of your instrument, the much more simple you can make your ring system. Why? If you're really going to do this at scale, yes, Psyche was hard, but we did one. If we're going to make 30,000 of them, it won't be as hard. So why
Absolutely.
not design the entire thing around a DSOC-like optical terminal?
Absolutely, that's an excellent question. And we could go right now to the website, change the parameter, and see what would come out is like just a few hundred satellites maybe. But the problem is like, can you really manufacture this at scale at the low cost that we expect? And so there's a trade-off between the cost and the performance that I'm not able to answer. Like I'm not a manufacturer, I don't know. So I took the more conservative approach just to show it's actually feasible even at this low performance. But if you increase the performance and trend toward Psyche, and you manage to keep it at low cost, then it's even better than this.
Pretty sure you could do 500 Psyche DSOCs for less than $12 billion.
Right.
So.
But no, for sure. But then you also have the problem of reliability. Can you have this operating, for the 10 years? If something fails, what happens? And you lose a lot of capacity. So this is like also have reliability built in.
You need a network of 5-meter telescopes on the Earth.
Well, it depends. If you link everything back to Starlink, then you don't need to use them. You're not doing direct to ground. You can go back to Starlink and have them distributed.
Fascinating stuff. Let's thank our speaker again.
Thank you.